Ladies and gentlemen, welcome to our today's webinar, Who Needs HD? Next Generation AR Guidance with ADAS and SD Maps, where we will learn how in a time when rural and other areas are lacking HD map coverage, SD Maps are sufficient for advanced AR guidance when fused with ADAS information drawn from vehicle sensors. My name is Sabine Sinkule. I'm an editor at Hütig Medien and write for the magazines Electronic Industry, Automobile Electronic, as well as E-Mobility Tech. And I'm also writing for our online magazine allelectronics.de. This webinar today takes place in cooperation with NNG. And now a few words about the housekeeping. This whole webinar will be recorded and will later be available for streaming in the webinar section on allelectronics.de. And you will all be muted during the whole webinar, but you can ask questions in the chat at any time. And we will try to answer as many as possible at the end of the webinar. But if there will stay some question unanswered, we will forward them to the speakers so they can answer them by mail. And now a few information about our today's speakers. So we have three speakers who are Dr. Martin Pfeifle, Dr. Andreas vom Felde, and Professor Dr. Niklas Zeller. Dr. Martin Pfeifle did his PhD thesis at the Ludwig Maximilian University in Munich, and he worked as a temporary professor for database system and data mining at Ruprecht Karls University in Heidelberg from 2006 to 2007. And from 2012 to 2019, he was the director of ADAS perception with Visteon. And now since 2020, he's working as a chief technology officer with NNG. Our second speaker is Dr. Andreas vom Felde, and he did his PhD in solid states physics at the University of Karlsruhe and worked as a postdoc at Bell Laboratories in Murray Hill, NG, USA for 3 years. And since 2011, he is MD of cross-border technologies in the Greater Munich area. And since 2022, he is General Manager of StratVision Europe and MD of StratVision GmbH. And Professor Dr. Niklas Zeller obtained his PhD degree 2018 from the Technical University of Munich. And between 2018 and 2021, he was working at Visteon in Karlsruhe and later at Artisense, which is a computer vision and AR startup co-founded by Professor Daniel Kremers, where he was leading the company's research activities. In 2021, Niklas returned to Karlsruhe, where he's now working at the University of Applied Sciences as a professor of signal processing and mobile robotics. And with that, I'll turn the floor over to our first speaker, Dr. Martin Pfeifle.
So again, a warm welcome from my side to this webinar on augmented reality and how we use SD maps and ADAS data for achieving applications like the one you see right now in the video. So basically, this is an application we developed at NNG together with our technology partners, and it shows you how we project guidance information into a front-facing camera so that it's nicely positioned there, and it helps the user really to get good guidance, information, and it also shows you users which might interfere with your planned trajectory, and they are highlighted then in order to avoid any accidents. And we did this all on top of our iGo Live platform, which is a general location-based service platform. And for this augmented reality applications, we also included our technology partner StratVision and the Hochschule from Karlsruhe, which contributed to this application. And in the following, I would like to show you 2 or 3 short videos from each company to give you a feeling about the companies, and then we go into more technical details. So let's start with NNG.
With our new iGo Live architecture,
So, and as I said, we included also StratVision into this platform. Last but not least, the Hochschule from Karlsruhe, they don't have voice on the video, but it shows you their core competency, which is basically creating a 6D pose based on GPS information, but also on visual inertial odometry. And based on this precise positioning, we are then able to position the guidance information and the objects in the 3D scene correctly. And based on all these three companies, we then create applications like the following, where we highlight POIs, where we present turn instructions on top of a front-facing camera on head-up display, and we are able to warn for objects which might interfere or which interfere with our planned trajectory, like these vehicles which are oncoming traffic. And then if no objects are there, then we can, turn left. Good. So this webinar will be given by Andreas from StratVision, Niklas from the Hochschule from Karlsruhe, and myself. And so Andreas will talk about visual perception and what StratVision is doing in this area. Niklas then talks about visual odometry. And I myself will talk about how to put these things together in an augmented reality application. Okay, Andreas, your turn.
So can you hear me? Hello?
Yes. Yeah, we can hear.
Okay. So a very warm welcome from my side. Thanks for the introduction. As you've heard, I've spent 30 years in semiconductor industry, in the past 10 years in automotive, and the past 7 years I've been the general manager for StratVision. So who's StratVision? My first slide here describes our company in a nutshell. The company is focusing on camera-based environment perception and provides deep neural network software stack for this purpose. It was founded in Korea almost 10 years ago, so it's no longer a newcomer to that scene. Rather, you may call it a matured startup or a small medium enterprise, since we have grown to more than 300 employees with worldwide presence, whereby main development remained in Korea and sales is outside, but also software algorithm engineers and field application engineers are dispatched in the regional markets from Japan to US. Likewise, we have a global span of investors. Some are Korea-based, but with Aptiv, ZF, and Asian originate from all relevant regional markets. You may call StratVision a matured startup, not only based on the company's growth, but also because our solutions are part of over a dozen SOPs and are on the streets in Korea, China, and also in German OEM models. Next page, please. Thanks. StratVision, or in short SV, provides on-site support worldwide with offices located in Detroit, San Jose, Düsseldorf, Tokyo, Shanghai, and various sites in South Korea, which enable us to respond quickly to customer needs and project requests. Finally, I'd like to highlight StratVision has an extremely strong patent base, all in the area of camera-based environment perception, among the top in autonomous driving and only second to big names like Lyft or Waymo. Next place, please. Important to reiterate is we focus on camera-based environment perception exclusively. So that is, we do not provide software for other sensor modalities, no fusion, no plan and act. And if we use LiDAR, we only use it for the purpose of ground truth generation. Why is that so? Years ago, we deliberately decided for clear focus. We decided not to compete with others being ahead in radar, LiDAR, or fusion software to become just another supplier. Rather, we wanted to be the best in the camera domain and a viable alternative to the elephant in the space, which is, needless to say, Mobileye. Next. StratVision provides everything you may ask for with regard to camera-based environment perception. That is why we are attractive for partners like NNG when they develop the next generation of augmented reality head-up display or center console systems, systems which go beyond providing only navigation systems by adding scene understanding, for instance, displaying hazards or predictions on traffic participants. As you can see on the slide, clockwise, we provide pedestrian detection, various classes of object detection, traffic sign recognition, traffic light recognition, free space detection, animal detection, parking space detection for line spaces as well as for spaces without lining, depth map functionality, and segmentic segmentation. Not shown here, since it cannot be covered all, are further functions like construction zone detection, general and static object detection, and even pothole detection, road condition monitoring we can offer. You may ask how we can support this bandwidth of functions, and the answer is we have developed all needed competencies in-house, and that is mirrored by a complete end-to-end tool chain. The next slide. We call that tool chain CompliKit for Complete Development Kit. It starts with a fleet of equipped vehicles for data generation operated by taxi companies or freelance drivers, mainly in Korea, in China, Japan, US, and various EU countries. They feed our StratVision Retriever, where we sample and select video data with a proper balance of weather, speed, type of road, number of objects, tech events, and so on. Then the data are pushed into our StratVision Annotator, which is our self-developed automated labeling tool. Well, no annotation engine is fully automatic, but we reach around about 97% productivity, which leaves about 3% manual work for human corrections and for ground truth generation and training data set, test data set generation. All that is the basis for our model building, which we call StratVision Deep Neural Network, or short SVNet. And I spare a further description. I assume you're very aware what needs to be done to master detection use cases. Let me stop with an important note. This CompliKit is open for third-party use and is licensed, so you can also use it with your own data in the cloud or even on your premises in case you do not want to give your data to the outside. Next page, please. In addition to extensive, comprehensive data recording and annotation, we keep a very close connection to all semiconductor OEMs. Why I'm making this a point? The answer is the competitive edge lies in the tight integration of hardware and software. By the way, Mobileye had the same finding. That is why Mobileye has developed their own IQ processor suite. With close connection, I mean we have insight into upcoming architecture changes and are even influencing architectural decisions before freeze of the chip design. Since years, we have made an exercise to be the worldwide first in porting to new SoC that become of interest in the automotive industry. In principle, we provide our SVNet on any SoC the customer asks for. Now, speaking of next generation augmented reality head-up displays, ask yourself what drives the acceptance and proliferation in the broad, mid, and low-end automotive market. In my eyes, it depends on three things. One is a good and valuable user interface, but second is a convincing performance, and third is affordable cost of this. So let me tell you, the tight integration of hardware and software is the key for pushing the performance on a given silicon footprint, as well as reaching optimum in cost reduction. With regard to user experience, I will touch upon this later on. Next slide, please. So here's our market approach. It's a fully customized one, your hardware and our software. Let it be the type of camera, its position, resolution, field of view, the ISP, color space, you name it. The SoC or even the allowed compute budget on that SoC all may be defined by the customer, including, of course, the desired use cases. And we provide the perception stack with fast time to market and state-of-the-art performance exactly to your specification. By the way, that approach is intentionally exactly the opposite one of Mobileye, which is a black box with hardware and software integrated in a take-it-or-leave-it offering. In addition, we provide that with maximum modularity and scalability. And speaking of the next generation head-up displays, flexibility and adaptability is another key in achieving affordable cost and minimum time to market. Next page, please. So very quickly, our SVNet software is focusing on 4 areas. One is, we call it ProDriver, is our driving software stack for passenger cars and commercial vehicles, also for people movers and robotaxis, where we are able to process up to 11 channels, that is 11 camera inputs simultaneously. Second is the Park Agent. It's our software stack for parking and maneuvering, also for passenger cars and commercial vehicles, with fisheye cameras. And recently we added the same for wide FOV cameras in order to include mid-range vision for urban driving. Third is immersive view, the topic of today, where we immerse into real-world overlays of our perception engine. And fourth, as I said, we have a complete development kit for our needs as well as for your use with your data. Next one, please. So here's a picture of it all. As StratVision, we provide a one-stop shop for camera-based environment perception, and we keep being at the forefront of automotive market needs in that domain. And we meet requirements of a broad variety of applications as they develop, from NCAP active safety functions to L4 autonomous driving, and from parking to infotainment. That way, we enable tiers and sometimes OEMs directly to succeed with fast time to market and low cost, while being able to differentiate themselves through technology. It's all designed to be highly modular and compatible, allowing system cost savings, flexibility, and scalability. And it fits into different architectures, as it was successfully ported on the full range of SoCs. The latest edition is Horizon Robotics chipset. Next page, please. So the flexibility and portability comes in very handy in our collaboration with NNG for next generation systems. This slide exemplifies what I've said so far. The idea is to have one SoC that integrates viewing and perception, rather than to deploy separate SoCs for various tasks. In short, the smart cameras are out, dumb satellite cameras are in the game. StratVision open and custom approach allows to follow current electrical architecture changes in the car towards domain and high performance computing, and to run its software stack in parallel with other software stacks on hypervisor and even on virtualized hardware. In other words, our adaptable solution and approach enables advanced driver assistance systems and car infotainment to merge seamlessly and silently. Next page, please. Thanks. So, Immersive View is our augmented reality tool for next generation augmented reality head-up display as well as center console applications. So now, how do you achieve a valuable and good user experience? In my eyes, for good user experience, we need several building blocks, and the most important three are the following. One is reliable detection. In the left box on the slide, there's a list of detection functions we can offer with top, mean, average precision and recall and minimum false positive. Second is precise localization of eager vehicle and detected object, as well as precise overlay into the real-world scene. For the one, we use CAN data, inertial sensors, horizon detection, and landmark tracking to determine ego motion. But I leave this part to the next presenter for a deep dive on this challenging subject matter. Regarding the precise overlay into the real-world scene, we use a 3D conversion of the 2D image frames, and we use an end-to-end deep neural network to come up with a very reliable depth map. And third, and that's the biggest challenge in my eyes, is a very low latency. I call it an imperceptible latency. Imperceptible means that for the human driver, it's a certain threshold where he doesn't see any latency between the overlay and the real world. That means it has to be certainly below 40 milliseconds. And here the efficiency of our network is key, plus some technical features like region of interest schemes, pruning, and pipelining. Next page, please. So once you have mastered all these three main challenges, you are able to display any type of hazard or predictions visually with high confidence. And you can extend this with all kinds of metadata you may want to choose, like distance information, time to collision, heading, relative speed, or visual indications of behavior predictions. And you can do this all in virtual 3D. I give you an example. If you look at the bottom right of the slide, where the car intends to turn left, a navigation chevron is displayed on top of all objects that are beyond the turn path, but appears behind all objects before the turn path. Next slide, please. So if time allows, I can show you samples of our depth map and segmentic segmentation, but I would like to confine myself to 50 minutes. I have 1 minute left. This is done on a Qualcomm 8155 chip. It's a 7 TOPS chips. But alternatively, next page, please. I welcome you to book a demo with our vehicles based in Germany, but not only in Germany. They are equipped with Qualcomm-based immersive view and in parallel with a forward-facing camera on a Texas Instrument TDA4VM to mimic typical setup configurations currently under consideration automotive industry. Next page. So with that, I'd like to hand over to my colleague. And let me thank you for your attention. And of course, I'm staying at your disposal for the Q&A session later.
Okay, so yeah, thank you very much, Andreas. Now, as we have seen Andreas talking about how we can use cameras to perform robust perception, I want to talk about the topic of how we can use cameras actually to perform very accurate localization. And before I dive into this topic, I actually want to give credit on one side to the computer vision group at Technical University of Munich, as well as artisans with whom basically most of the work which I'm presenting here was developed. So next slide, please. And before I go into the topic, I actually first want to present what I see as the main advantages to perform camera-based localization. And one thing which I see there is, for instance, that we have very small and passive sensors, and therefore we also have very low power consumption. Furthermore, due to the mass market production of those sensors, they are much cheaper compared to LiDAR systems, for instance, which we could use for localization, or very expensive INS systems. And another very important point is that actually any modern car already is equipped with cameras. So therefore, we don't even need any additional sensors to perform accurate localization of our vehicle. Next, please. And if we look into the classical paradigm of visual autometry, which are so-called indirect methods, we go the pipeline that we record a video sequence. From this video sequence, we extract what we call feature points. So we basically pick corners in our images and we match them across subsequent images. And now using those corner points, using those key points, we can perform optimization by optimizing a so-called reprojection error and estimate the camera poses as well 3D coordinates of those key points. Next, please. Now, about 10 years ago, so-called direct methods came up, where we have to ask ourselves the question, do we actually need this feature extraction step, or can we just skip it? So basically what we do here, we just take any point, any pixel in our image and try to project it from one frame to another frame, and not minimizing a geometric reprojection error, but minimizing a photometric error. So we try to estimate the pose and a 3D reconstruction of the environment by minimizing the intensity difference between the pixels of subsequent images. Next slide, please. And now I hope the video is starting. Yeah, I hope you can see the video. But by going this approach, by going those direct methods, we can do something what we see here. So we can just take a single camera, and based on the images which we record by the camera, we are able to quite accurately track the motion of this camera, so estimate the position of this camera. And as kind of a byproduct, we also get, it is a sparse, but in general, a quite detailed reconstruction of our environment. And what you see here in this video, if you look at, so we basically walk in a loop, and what you can see here that we can estimate our position with quite a small arrow, with quite a small drift. So next slide, please. However, if we just use a single camera, we have certain drawbacks. And one thing is that a single camera basically is not able to observe the scale of the scene. And therefore, if we are estimating a trajectory, the trajectory also won't have metric scale. And even more important, since we are not able to observe the scale also will be drifting. And this we see in the next slide. So if we estimate a trajectory, we will see that there can be regions where we underestimate our ground truth, and in other regions we are overestimating our ground truth. So in general, we get a trajectory which is in itself distorted. So next slide. And now we have to ask ourselves, how can we overcome this problem of scale ambiguity? And of course, the most obvious thing is to use a second camera, so we can build a stereo camera system and perform visual odometry or SLAM based on this stereo camera. Alternatively, or additionally, we also can integrate an IMU and use the IMU measurements and the dynamics of our vehicle to observe the scale of our scene and integrate all of this into our visual odometry pipeline. And last but not least, we can also use deep learning. So this is also something which Andreas showed, that we can train a neural network and basically predict a depth map from a single image. And now again, we can integrate this information into our visual odometry system and thereby build a system which basically is able to observe the scale and therefore doesn't have any scale drift anymore. So next slide, please. So by doing all this, what we are able to do is building a visual odometry system which is able to accurately estimate the position, the motion of our camera. However, we only are able to do this in a local frame. And the question is, how can we get localization with respect to a global frame? And if you go to the next slide, we're going to see the video which we have seen already in the very beginning. So basically what we do here, we take our visual odometry system. So this is a stereo inertial odometry system. So we have a stereo camera and we have additionally IMU measurements. And now what we can do is we integrate GNSS measurements, highly accurate GNSS measurements. And this way we are able to localize ourselves or our vehicle with up to centimeter accuracy. And we can not do this only in open sky conditions, but also we can go into a parking garage, for instance, or into a tunnel. And we are able to localize with very minimal drift, so with a very minimal error, because we have our reliable and accurate visual odometry system, which continues tracking the relative position of our vehicle. And if we go to the next slide. So, I mean, this is something which we can do, but in general, we have some drawbacks. And one drawback, for instance, is that global positioning, we only get in open sky conditions. So therefore, if we think about we start the system in a parking garage or in a tunnel, we won't be able to get our global position. And we have to wait until the point where we have open sky conditions and where we can get global position measurements. Furthermore, to get those accurate measurements, we are relying on real-time correction data, which have to come over the internet. So we always have to have an internet connection for our accurate positioning system based on GNSS. And if we go to the next slide, we have to ask ourselves how can we overcome this problem. And one way to overcome this problem is doing something which we call map-based localization. So the idea is basically that we pre-generate a map. We are building a map in advance, and now we want to have our visual odometry system, which is able to localize within this map. So basically, the goal is to estimate a 6 degree of freedom path with respect to the pre-built map. And here on one side, the map can be a collection of landmarks. It can be 3D points, just 3D key points, or it can also be just post-reference images, so that we have recorded images and we know the respective pose of those images. And the goal now basically is what you see in the image here, that we have to find a way how we can establish correspondences. So how can we find the correct key point or the correct landmark between two different, or for the same sequence, between two completely different weather conditions, different seasons of the year, and so on. And if we go to the next slide. So if we build such a system, we are now actually able, as we see it here in the video, to globally localize with our visual odometry system with respect to a pre-built map. So maybe you can see it very tinily on the bottom left. We see the position of our vehicle in a global map, so in Google Maps basically. And on the top, we still see our visual inertial odometry system, which is tracking the relative position of our vehicle. And now what you're going to see in a second is that this way we are able to build a system which is quite robust, and it's robust to changes in weather conditions. So basically, you see here the image of the live run, and in a second you're going to see the image which was used when we were recording our map. So basically, we are able to extract features, to extract key points, which are quite invariant against those weather and lighting changes, and therefore we can enable a quite robust global localization system by using only a single camera and the map information which we have to have generated in advance. And now if we go to the next slide. So what I want to show you now additionally, so this is on one side how we can use visual odometry for performing accurate localization. However, we can also go a step further and think about how we can still use visual odometry and use SLAM for other tasks. And if we go one slide further, so what we actually can do is we have seen from our visual odometry system, what we get on one side are the poses of our camera. So we are able to estimate an accurate position of our vehicle. And kind of as a byproduct, we get a sparse reconstruction of the environment. However, it might be the case that we want to have an accurate and detailed reconstruction of the environment. And therefore, what we can perform is something which we call dense 3D reconstruction. So we basically can take the sequence of images and the corresponding poses, which we estimated with our visual odometry system. And now we can train a deep neural network, which is able to estimate a dense depth map based on all this information. So based on the image information, we get the depth map, which you see here on the top right. And additionally, what we also can see is that we can have inconsistencies in our images from moving objects. So we are even able to detect moving objects in our environment just from the image information. And if we go to the next slide. So by using such a system, what we are able to, by using only a single moving camera, we can generate quite detailed 3D reconstructions of our environment, as we can see here. So this is all generated based on a neural network, and the input is just a video sequence, just a sequence of images. And since we are able to also detect moving objects, if we build such a reconstruction, we can detect those moving objects, and basically we can just remove them from the reconstruction, because otherwise they would generate artifacts. As you can see it here in the video, we know which points correspond to moving objects, and we just remove them from our scene, and this way we get quite easily a very dense and detailed reconstruction of our environment. Okay, so I think we can go to the next slide. In the end, what I also want to present is a data set which we recorded, because we have seen that we can use visual odometry to perform localization. We can go one step further and perform dense reconstruction, so get quite detailed reconstructions of our environment. However, we also want to push the research and the development in visual odometry further. And therefore, together with TOOM and Artisense, we recorded a new data set, which is meant to enable research on simultaneous localization and mapping, as well as visual odometry. And in this data set, what we did, we recorded more than 350 kilometers of video sequences, and we tried to record them in a very wide variety of weather conditions, of lighting changes, and even in different seasons of the year. And one unique point about this data set, that all the sequences which we are having, they are quite accurately aligned up to centimeter accuracy using RTK GNSS measurements. And now if we go to the next slide, what we can do by this, what you see here in the video, so we have 4 times exactly the same environment, and the images are really perfectly centimeter aligned. And so now we can use this data set to basically develop new methods for map-based localization, for instance, and we are also able to use the data set to benchmark basically existing methods. And if we go to the next slide, this one, and if we run the video, so we tried to record those those sequences in as many different environments, because there are quite different challenges if we are, for instance, in urban areas, if we are on a highway, or if we are in countryside areas, or even in the parking garage, which we can see here on the bottom right, where we have quite repetitive structures. So therefore, we want to use this data set, and we released it to the public to make it possible to do more research in this direction and to develop more robust and better algorithms for localization, for 3D reconstruction, and everything related to SLAM. And with this, I'm at the end of my part of the presentation and want to hand over to Martin.
So thanks, Andreas, and thanks, Niklas, for outlining what you do in visual odometry and visual perception. At NNG, we bring things together here. Before we go into more detail, let me start with one slide about NNG. So NNG is a navigation software provider. Our software runs in more than 20 million vehicles. Majority of the top automotive groups are customer of NNG. As I said, we are a software company, so it's also natural that the majority of our employees are software engineers. We are located in more than 9 countries. Currently, I'm here in Budapest, but we also have an office in Stuttgart, for instance, and in Shanghai. We regard ourselves as innovation leader in the area of navigation and also adjacent areas like, for instance, augmented reality. So let's see what we do here from a technical point. So at NNG, we developed this iGo Live platform, a location-based service platform, and we bring here different data sources together. For instance, SD maps, so the standard definition maps, which you might know from our navigation system or from Google Maps. Then HD maps, which are typically used also in self-driving. Then sensor information coming from visual perception, for what Andreas outlined, and also dynamic information coming from services like TPEC or V2X. And our goal at NNG is to make manual driving safer and more convenient. And for this, we developed something called an intelligent co-driver, which goes hand in hand with our augmented reality application. So the iGo Live platform, as I said, is a location-based service platform, and it consists of several applications leveraging then different components which are running under the hood. iGo Navigation is our core product. It's, as I said, we are a navigation company, and obviously we are also focusing on EV navigation as one of the already existing trends in the industry. So we do here long distance routing for EV vehicles. We depict the range polygons. We tell you which charging stations to use, how to combine this with user preferences for POIs, and so on and so forth. And we basically have all the features required by the market for navigation. Another product we developed for this iGo Live platform is called iGo Ahead. It's basically an application which provides map data and service information along your most likely route. And what we do here is explained in this short animated video. So our cloud is connected to data provider clouds, which might come from data providers like here. We fetch then the data from here, from the clouds, and in the car we run a positioning engine or a localization engine, which gets GNSS information, IMU information. We compute a position, and based on this position, we ask our server for data. Depending on the car configuration, we might send down only speed limits and map data in order to support use cases like, for instance, intelligent speed assistance, which then is distributed inside the car via ADAS V2 to other ECUs. Other cars might also use ADAS data like slope data, curvature data, and then they get these packages. A third car might also use dynamic information like construction zone information or even weather information, and all this is only then provided to the car along the most probable path and not complete tiles. So it's very, very low bandwidth is required for this application, and it's tailor-made for supporting these kind of ADAS application and NCAP applications. And the last application, what we want to discuss today is iGo AR. And as said already, we are working here together with technology partners like StratVision and the Hochschule from Karlsruhe to develop applications which help the user to navigate in complex environments. And one use case which we did 2 years ago, or one product we developed 2 years ago, was together with HD maps. And what we showed at IAA in Germany is that we map then these guidance information very precisely to the front-facing camera or a head-up display. And what you see here, this green chevron, is basically the center line of an HD map. And by doing this precise positioning outlined by Niklas, we can then basically map the HD map information into this scene and do lane departure warning and other features like also lane guidance here very precisely and in an intuitive way. The problem with this HD map is that they are very expensive and that they are only available in certain areas. And because of that, we decided to go away from these HD maps and look into other opportunities to help the driver with augmented reality guidance. But before we talk about the use case without HD map, here's another example from our iGo Live platform where we also use HD maps. So on the top right, you see then an augmented reality scene. On the bottom right, you see a 3D scene and a top-down rendered image. And our navigation system can obviously provide the information in all of those three output formats. And in this example, it is depicted that a slow-moving vehicle is detected via visual perception as outlined by Andreas. And we know and we position that car so that we know it's on the right lane of this exit lane. And our ego vehicle, which is behind this vehicle, it wants to turn right. And our guidance information tell him at the beginning, okay, there is enough space behind this slow-moving vehicle, so please change to the rightmost lane now. But as we don't do self-driving, but we advise manual drivers, the manual driver might or might not follow our instructions. In this case, he ignores it. He simply doesn't position himself behind the vehicle. And if we realize that there is not enough space anymore, then we tell him, okay, now please stay on the lane and don't turn right immediately, but only after we have overtaken this slow moving vehicle. And by doing this, we bring together then visual perception, HD maps, and render this in various output formats like in augmented reality or in 3D scenes. But as said, the problem with this HD map data is that it's not available in a lot of areas, and it's also rather expensive. And therefore, we looked into what can we do now if we take out this HD map from the equation. And we basically developed then a complete new stack, which is explained here. And it looks very complicated, but let's go through it so that you understand what we are doing. And then you will see the result of what we are doing in the last video on the next slide. So our iGo AR application consists of the following 5 building blocks, basically. So it's basically this ADAS AR perception, which is what Andreas outlined. So StratVision detects all the objects. The lanes creates a depth map, and based on all this information, we know what's going on around us. Then what we also need is this precise positioning and pose. So Niklas showed that he is using visual odometry, also the camera, but he also uses the GPS information and IMU information, and all this is now required to generate this precise 6D pose. What we now do is that in situation analysis, we bring together these worlds. So we first of all need to take the objects detected by Andreas, by StratVision. We need to map them as well to the map. So we need to know whether an object is on the lane, on which lane it is. So because we have the rules whether objects on certain lanes interfere with our own trajectory. So we also need the mission statement from the navigation. So we need to know where the car is heading towards in order to decide whether an object interferes with what we are planning. And now, based on all this information, we decide then which objects to highlight and which objects to warn for. And if we do that, we create a 3D scene in front of the vehicle. This 3D scene consists now of the objects we want to warn, but also the guidance information. You remember what Andrea showed with this navigation chevron, which you also see here. So this is all positioned in a 3D scene, and we need the precise pose in order to have the camera, so that if we render this 3D scene, that it's then depicted nicely on a head-up display or on top of a front-facing camera. So in the last step then is the rendering. And in rendering, we basically distinguish between head down, which is basically on top of the front-facing camera, or head up, where we then depict it projected on the windshield, and might also take driver monitoring information into account to correct for the head movement and the eyes of the drivers. So yeah, now bringing all this together, we can then generate these kind of applications, which you saw at the beginning, and we also saw some videos here, where we depict here the guidance information, where we warn for objects. And we think that this technology, which is based on AI-based object detection, as outlined by StratVision, precise positioning, as shown by Niklas, and in general is using a lot of autonomous driving technologies, because the technologies shown are more or less one-to-one applicable for self-driving. And we bring these things then together in augmented reality-based guidance applications, with the goal again to make manual driving safer and more convenient. So yeah, thanks a lot for your attention, and it would be good if Andreas and Niklas switch on the cameras again, and we are now open for your questions. Thank you.
Write your questions, and I'll see if we answer them. And we already have one question for Dr. Martin Pfeifle. The question is AR the only visualization format you support, or can iGo AR display the data?
I can, Sabine, I don't know whether it's on my side, but you're breaking up. I don't know. Did the others understand it properly, or maybe you can repeat the question?
Do you have problems with hearing
No, it's
me?
better. It's better.
Okay, now it's better. Okay, then I will repeat the question.
Yes,
sorry for
thank
that.
you.
So is AR the only visualization format you support, or can iGo AR display this data in other ways as well?
You know, I showed one slide where we showed the content on top of an augmented reality in an augmented reality scene, but we can also render it for instance, in a navigation environment. So, and this was shown in this 3D scene where we use the HD maps on a top scene, and then basically render it on a navigation system in the IVI stack. So all the information like warning and is obviously can be done and shown independently of augmented reality. It can be even non-visually warned, you know, and with guidance information like, watch out, there is a car coming from the right, or don't take over, or take over this vehicle now. So it's not necessarily bound to augmented reality, but obviously we see a huge advantage in this augmented reality situation. Examples which I probably have not shown in this video were, if we look for house numbers and the user enters his final destination as a house number, and we show this in the real scene, in augmented reality scene, the user knows exactly which house he has to stop. If we show it on a map only, he still has to do this transfer from the map, what he sees, to the reality. And so we see a lot of advantages in augmented reality, but a lot of the information we can also provide to the user in HMI, in other HMI ways.
Okay, thanks for answering the question. And we have another one, again for Dr. Martin Pfeifle. What other use cases can you imagine the software being used for?
So as I said, I mean, I think a lot of the applications we showed is the technology is very closely related to self-driving. So like what StratVision is doing, 80% of their software can be used for level 2 or even level 3 driving, the self-driving. So I think that's basically the one use case. Then, I mean, we talk about other use cases as well here at NNG, which I cannot reveal right now. But I think the augmented reality use case is coming, is a topic which comes in general in the industry, right? But that's it basically. I can't go into more detail here.
Okay, thank you. Then we have another question. How do you see the market chances of next generation augmented reality head-up displays? I guess that's maybe for Dr. Andreas vom Velde.
Yeah, I think there's a big potential to hit the commodity market. So not high-end vehicles, but medium-priced and even low-priced vehicles. So of course, if you're not willing to make your cross as a customer for a head-up display, you might not choose the next generation head-up display. But I think head-up displays will become a standard feature. And there's a big chance that also the next generation head-up displays becomes a standard feature. And as I tried to explain, the key is really doing it all at low cost, using what we call mid-segment SoCs, not expensive NVIDIA-type chips, but those that are certainly one-digit teraops and are in the ballpark, let's say, of $20 bill of materials cost for the silicon footprint. That is doable. What I've skipped showing in my presentation, the video that was done on a Qualcomm chip, and important to notice, we only use a small fraction of the entire Qualcomm chip, not all the 7 teraops. So this system can be built at a suitable cost. So therefore, I think there are chances to hit the mass market.
Okay, thank you. Then another question is for Niklas Zeller. How does SLAM differ from visual odometry, and why do you favor SLAM?
So how does SLAM differ from visual odometry?
Exactly.
Is that in general, I would say today they are almost so the terms are almost used as synonym, but like from back then, the idea of visual odometry is mainly about estimating the pose of a camera basically, and thereby the pose of the vehicle. And SLAM is more in the direction that I want to localize myself, so I want to estimate my pose, but at the same time I want to build a 3D map of the environment. But what we have, or what I've shown in the beginning of the slides, that if we look into today's visual odometry method as a byproduct, you always estimate a 3D reconstruction of the environment. So it's more about how you later going to use the map which you are building, if it's only a byproduct which you need to get accurate poses, or if you later make also use of it. And then, I mean, you can think about things like what we call loop closures, for instance, that do you store the information of the map? And if you come back to a location, will you reuse the map which you have built before? So therefore, I would say that if we go in the way or in the direction of map-based localization, this is rather a way of doing SLAM, because we started to build a map and now we are reusing this map. So this is how I would differ the terms. But today mainly in research and also in industry, the terms are almost used as synonym basically.
Okay. And then another question for Andreas vom Velde. What do you think are the key technical challenges for augmented reality head-up displays to overcome?
Okay, yeah, basically it's a summary of what we have talked about the past 45 minutes. So you have to do reliable detection to start with, but I think that is a standard feature in the market, has been a proven technology. So the essence is here to perform high KPIs at very low cost. But then it's important that you do excellent self-localization of your car, what Niklas just explained, and you do have a rendering machine that your overlay is exact on the real world. And third, there should be no palpable latency. So when you have an overlaid hazard or prediction warning, it should not be 1-2 frames too late compared to the real world, because then the user experience is, you sense the lag, and that is not very comfortable. If you master those three, then with the building blocks that Niklas explained and Martin explained, when you put this all together, you get a really nice and I think a valuable addition to today's features in the car.
Okay, thank you. That brings us to the end of our webinar. Thank you very much to our speakers again, and thank you for your attention and your interest. As I already said, you can stream the webinar on allelectronics.de pretty soon. Yeah, have a nice day. Goodbye.
Goodbye.
Bye-bye.